Hello everyone, thank you for the opportunity to talk here. So as it was said, I was going to talk about the constraints that could be given by on the size of actual dimensions by observing compact stars. Okay, sorry. No, it's okay. So as it was mentioned a lot of times, neutron stars are remnants of supernovae that are supported by baryon degeneracy. And why they are very useful to probe physics is because they have such large densities that and low temperature with this that this kind of environment is not available on Earth otherwise. And what we did is that we assumed that there is one extra compactified dimension in addition to the 1 plus 3 plus 1, so 1 plus 3 dimensions. And this is based on a Kaluza-Klein model. So here we assume that this extra dimension that we added is spatial, and it has a finite size on the orders of a few Fermi. And the assumption is that particles could step into this extra dimension if they have enough energy. They need this energy because in this dimension, a periodic boundary condition will emerge. So they will need to have quantized momenta. And the smaller the size of the dimension, the bigger this momenta. So particles need a lot of energy to be able to step into this dimension. So as we can see here, the energy in the fifth dimension will be partly the mass of the particle, the k momentum, which is just the momentum in the usual free spatial dimension, and there's going to be an extra term, which is the n over rc, which is n is the excitation number that these particles could have, and rc is the size of this extra dimension. And if you translate this into the the normal description with the 1 plus 3 dimensions, then this will mean that particles could have a different type of mass, which consists of this extra excitation and the ordinary mass. So what we did is that we choose one particle as the base, which was the neutron for us, and we give the neutron extra excitations. So basically this produced a different kind of spectrum, which can be seen on the right. So these are the different masses that we get for sort of hadronic particles, and we use these to construct an equation of state from this. Thanks. So we solved the Tolman-Oppenheimer-Volkoff equation with an equation of state for the energy density and the pressure, and the two boundary conditions, of course, are the central energy density of the star, and the pressure should be 0 or a minimum at the surface of the star, and that's how we get the markers, as was already mentioned a lot of times. So onto the equation of state, we used a linear potential that depends on the baryon densities. So there's going to be a repulsive interaction to mimic the strong force, and the strength of the interaction is given by this constant psi, and it depends on the baryon density n. And using this, with the thermodynamic quantities can be derived from the thermodynamic potential, and the extra dimension will go into these equations by adding basically the new spectra that was described before, this new mass spectra of the particles into this, instead of some other particles with other masses. And the interaction is just a shift in the chemical potential and also an extra interaction term. The relativity in this extra dimensional description is, we had multiple assumptions, but for the TOV equation we assumed spherical symmetry, time independence, and an isotropic, relativistic ideal fluid. And for the extra dimensional part, we assumed that the normal 4 dimensions don't depend on this extra term here, so it won't affect anyway the other part of the metric, and that causality postulate should hold, and we also have full Killing symmetry. So here are some graphs of the equations of states that we gained this way. So the colors correspond to different interaction strengths. The blue one corresponds to no interaction at all, and we can see that so the little arrows show that how we varied the RC, which is the size of the extra dimension. So if you have no interaction, this variation due to the size of the extra dimension is much more dominant than for if we have a large interaction. In this case, the variation due to the different compact dimension sizes could be much smaller. And here we added some extra equation of states that was taken from the Compose website. These are more refined equations of state. We can see that for larger energies, those equations of state of ours that have higher interaction strength approximates this better, but for lower energies is the non-interacting one that approximates this better. And here are some MR diagrams that we created this way. So again, here the colors correspond to the different interaction strengths. Blue is the non-interacting way. This produces way too small stars. And as we go up and up, the dependence on RC, which is again indicated by arrows, is much smaller. And this is how the interaction strength grows. And here we added some measurement data and also some plus equations of states. And we can see that it is possible to create, with this type of model, realistic stars with realistic mass and radius relations. And we can change the position of this black curve by, so this is set for some certain psi, and if we change the size of the extra dimension, this could be tuned. So in summary, we built up a model with the possibility of probing beyond the standard model of physics, and we use one extra spatial compactified dimension where ordinary mass can be described as a quantized 5-dimensional momenta in the 5-dimensional description, and we used effective nuclear field theory with linear repulsive potential, and we can see that this is possible to build realistic stars with this type of model. Of course, it's a very simple model. And given that there are more precise data on neutron star radius and masses, it could be possible to give constraints on the radius of this extra dimension. Thank you for the attention.
Any questions for the speaker?
Yeah, thanks for the nice talk. I was wondering, what's the rationale behind the potential that you chose here?
So this is a very simple one, actually. So we try to find the simplest possible, so it's just a linear one.
Do you expect that kind of potential in like a generic extra dimension model?
I mean, I don't think that we are expecting that really to be very realistic, but the point was to have the simplest model possible.
And just the last question, do you have any thoughts of what this would look like if you increase the number of extra dimensions?
Yes, that's an interesting question. And the answer is again the same, that this is the simplest, but of course we could have many more different dimensions with different topologies, so maybe tori or something.
So it would be harder?
Yes.
Actually, when you consider the extra dimension, does the equation of state becomes softer, I assume, right? Because you can put some particles in the extra dimension and lower the Fermi pressure. Is that Is that correct? Or
Yes, basically. So the more we can also change the number of particles that we put in it. So it also affects, and the bigger the dimension, the more particles could possibly appear because there is a dependence on the sorry, where is it? So the larger the RC, the smaller the gaps will become. So there are more particles could step in, and yes, it will. I think it will produce smaller stars actually.
okay, and as you increase the energy, shouldn't you see some sort of like a kind of like kink? I mean, in the sense like that at the energy scale where you probe the extra dimension, I mean, something dramatic changes, right? So should I see some sort of like a kink actually when you probe the extra dimension?
Yes, well, there is. I don't have such graphs, but for example, in the speed of sound, you can see that there are some kinks when the extra particles step into the picture.
Okay, all right, okay. Any other question? Yep.
I have a question related to the equation of state. So you compute 5-dimensional integrals, right? But to solve the TOV equations, you actually need the 4-dimensional quantities. I guess this is in the plot when you saw the energy density versus the pressure. These are the 4-dimensional quantities. The question is how you go from the 5-dimensional quantities to the 4-dimensional ones.
So actually, what we did is really that the particles that we put into it, it's really just the mass that changes, because the particles can step in the extra dimension, but there's one base, which is the neutron, and then there's it gets extra excitations, and in the usual 1 plus 3-dimensional treatment, it's just particles with different masses. So we don't really need to calculate with 5 dimensions.
Okay, thank you.
All right, so if there are no more questions, let's thank our speaker and all the speakers of today.